Okay, this lecture covers Chapter 7 of your textbook on supervised machine learning. And first, we'll talk a little bit about the learning objectives for this chapter. In this chapter, we're going to look at how supervised machine learning works and why it is so important in cybersecurity. By the end of this lecture, you should understand the basic structure of a machine learning problem, including the role of data, tasks, and performance measures. You should also understand how supervised learning systems use labeled examples to train models that can make predictions about new data. And we will look at two common types of models used in supervised learning: decision trees and linear classifiers. These models appear frequently in real-world systems, including tools used for phishing detection, malware classification, and intrusion detection. The goal is not to make you into machine learning engineers today, but to help you understand how these systems work conceptually so that you can reason about them as cybersecurity professionals. And finally, we will talk about one of the most important issues in machine learning: overfitting. A model can appear to perform extremely well on training data, but fail when confronted with new data. Because attackers constantly change tactics, cybersecurity models must be able to generalize beyond the examples they were trained on. And we will also discuss evaluation techniques such as training and test splits and cross-validation that help us measure whether a model is actually learning useful patterns. And now we'll talk about components of a learning problem. So every machine learning system can be understood in terms of three basic components: the task, the data, and the measure of improvement. The task is the behavior that we want the system to improve over time. In many machine learning systems, the task is classification, such as deciding whether an email is a phishing email or a legitimate email, or whether a file is malicious or benign. The second component is the data, which represents the experience the system learns from. So machine learning models do not invent knowledge on their own. They learn patterns from examples. In cybersecurity, those examples might include labeled malware samples, historical phishing emails, or network traffic logs that have been categorized as normal or malicious. And then the final component is the measure of improvement, which tells us how well the model is performing. For example, we might measure how often the model correctly identifies phishing emails or how accurately it detects malware. Without a performance measure, we have no way to tell whether the system is actually learning anything useful. And this diagram shows the overall architecture of a learning system. At the center is the learner, which receives data and produces a model. You can think of the model as a set of rules, parameters, or mathematical relationships that allow the system to make predictions. The learner is trained using experiences or data, which contain examples of the problem we are trying to solve. Once the learner has built a model, that model can be used by a reasoning component to answer questions or make decisions. For example, a trained model might analyze a new email and estimate the probability that it is a phishing email. Another important part of the system is background knowledge or bias. Every learning system has some assumptions built into it about what kinds of patterns it expects to find. These assumptions guide the learning process and determine what kinds of models the system can produce. One of the most important ideas in machine learning is that success is not measured on the training data. Instead, success is measured by how well the model performs on new examples that it has never seen before. The slide gives an example with two hypothetical agents. Both agents perfectly classify all of the training examples, but they make completely different predictions about new cases. This illustrates a key point. Simply memorizing the training data does not mean the model has learned the true pattern behind the data. In cybersecurity, this issue is especially important. A model might correctly classify every malware sample in its training data set, but still fail to detect new malware variants that were not present during training. That is why we focus on models that can generalize to unseen situations. In machine learning, the word bias has a specific technical meaning. It refers to the tendency of a learning system to prefer one type of hypothesis or model over another. This preference is not derived from the data itself. Instead, it comes from the assumptions built into the learning algorithm. Bias is actually necessary for learning to work. Without it, the system would have no basis for choosing one possible explanation of the data over another. For example, a learning algorithm might prefer simpler models, or models that use certain types of mathematical relationships. In practice, the effectiveness of a particular bias is an empirical question. We evaluate different approaches by testing how well they perform on real data. In cybersecurity applications, the best models are usually those whose assumptions allow them to capture meaningful patterns in attacker behavior while still generalizing to new threats. And machine learning systems depend heavily on the quality and completeness of their data. In practice, data is rarely perfect. Some features may be missing, some values may be incorrect, and sometimes the available information simply isn't enough to determine the correct classification. For example, imagine trying to classify emails as phishing emails or legitimate emails. If your data set does not include important features like domain age, link structure, or sender reputation, the model may struggle to detect the correct patterns. In other cases, labels themselves might be wrong, such as when a malicious email is mistakenly labeled as safe. These limitations introduce uncertainty into the learning process. When the data does not contain enough reliable information, the model may detect patterns that exist only in the training data set but not in the real world. This problem leads to one of the most important challenges in machine learning, which is overfitting, which is a concept that we'll discuss later in the lecture. Now, supervised learning is one of the most common approaches used in machine learning. In supervised learning, the system is trained using labeled examples, meaning that each training example already includes the correct answer. Each example contains input features which describe the object or event we are analyzing, and target features which represent the outcome we want to model or the outcome that we want the model to predict. That would be the target features. During training, the model examines many examples and learns relationships between the inputs and the target output. Once training is complete, the model can be applied to new data where the correct answer is unknown. The system uses the patterns it learned during training to predict the most likely outcome. Depending on the type of problem, the output may be a discrete category, such as phishing or legitimate, or a continuous value, such as a probability score. And now let's apply this specifically to cyber detection. Supervised learning is widely used in cybersecurity because many detection problems can be framed as classification tasks. Security systems often analyze large volumes of historical data that have already been labeled by analysts or by detection systems. For example, malware detection models are trained using files that have been labeled as either malicious or benign. Email filtering systems use labeled data sets of phishing and legitimate messages. And likewise, intrusion detection systems analyze network traffic that has been categorized as normal activity or malicious behavior, such as an intrusion. And transactions can be labeled either as fraud or legitimate by, for example, a banking system might automatically label a transaction as fraud or suspected fraud versus legitimate. And so with labeled examples like this, the model can learn patterns from these labeled examples and can then identify suspicious activity in new data that is never seen before. And many modern security tools rely on supervised machine learning to automatically analyze files, network traffic, and user activity at a scale that would be impossible for human analysts alone. So that's why it's such a powerful tool, machine learning, supervised machine learning in the field of cybersecurity. Now let's talk about evaluating predictions. So once a model begins making predictions, we need a way to measure how accurate those predictions are. And this slide introduces the basic idea of prediction error, which represents the difference between the predicted value and the actual observed value. In a classification problem, the model might simply predict the wrong category, such as classifying a phishing email as legitimate. In other situations, the model may produce a numeric prediction, such as a probability score, and the error reflects how far that prediction is from the correct output, or I'm sorry, from the correct outcome. And different applications use different error measures depending on the problem being solved. So some measures focus on the number of incorrect predictions, while others measure the magnitude of the prediction error. The important point is that machine learning models must be evaluated systematically so we can determine whether they are actually improving performance. So now let's talk about training and test sets. To evaluate whether a model truly works, we divide the available data into two separate sets, a training set and a test set. And this is referring to the available data like a historical set of data that's already labeled. And the training set is used to build the model by allowing the learning algorithm to analyze patterns in the data. The test set, however, is never shown to the learning algorithm during training. Instead, it is used only after training is complete to measure how well the model performs on data it has never seen before. And this separation is essential because it allows us to evaluate whether the model has learned general patterns or simply memorized the training examples. In cybersecurity applications, this is particularly important because attackers continuously change their techniques. A detection model must perform well not only on past cyber attacks, but also on new attack variants that appear in the future. And before I move on to the next slide, I think I'll elaborate a little bit more. If you have a data set that's already labeled for a classification task, like for example, phishing emails versus regular emails, and it's a very large data set, like 10,000 emails, you might break that data set. Traditionally, about 70% of it you would use in the training data set, and you'd reserve 30% of it in the test set. So you would run your machine learning model after you've created it. You would run it on the training examples and allow it to train to try to identify features that distinguish between the two groups, the phishing emails and the regular emails. And when it's finished training, you would then give it the test set, and it would test its ability to predict whether each sample in that set is phishing or regular email. And then, because it's a labeled set, it would compare its prediction that it made from its algorithm to the label. And then the test set could then report on the effectiveness of the model in terms of what percentage of items, of pieces of data from the test set it was able to accurately predict. So that's how the training and test sets are actually used after you create them from a large labeled data set. So now let's apply that concept to cybersecurity and talk about a little more about how security models must be able to generalize. So one of the biggest challenges in machine learning for cybersecurity is that attackers constantly change their tactics. A model that works perfectly on past data may fail completely when it encounters a new variant of an attack. For example, a phishing detection system might be trained on historical phishing campaigns. The training data set might include thousands of labeled examples of malicious emails. However, attackers quickly adapt. They change domain names, they alter message content, and they modify attachments in order to bypass detection systems. So because of this, security models cannot simply memorize past attacks. Instead, they must learn patterns that generalize to new situations. And separating training data from test data helps us evaluate whether the model has learned useful patterns or simply memorized examples from the training data set. And now let's talk about decision trees. So a decision tree is one of the simplest and most intuitive machine learning models. It represents a sequence of decisions that lead to a final prediction. Each internal node in the tree represents a condition based on input features, and each branch represents the outcome of that condition. As the model evaluates an example, it moves through the tree by answering a series of yes or no questions. Eventually, it reaches a leaf node, which provides the final prediction or classification. Decision trees are particularly appealing because they resemble if then else logic, which is already familiar to many people who work in computing and cybersecurity. This structure makes decision trees relatively easy to understand and to explain compared with more complex machine learning models. And this slide shows a simple example of a decision tree built from training data. The tree evaluates several features and uses them to determine whether a particular action should be taken. Each decision point in the tree corresponds to a feature in the data set. For example, the model might examine whether a message comes from a known author, whether the thread is new or part of an existing conversation, or whether the message is short or long. By following a path through the tree, the system eventually reaches a leaf node that represents the predicted classification. Even though this example is simple, it illustrates how machine learning models can transform patterns in data into a structured decision process. And then applying this to a cybersecurity example, we'll talk about decision trees and phishing detection. First, talking about some example rule logic, and then on the next slide, we'll look at a visual model. So in cybersecurity, decision trees can represent security decision rules used in automated detection systems. For example, a phishing detection model might evaluate several features of an email before deciding whether it is suspicious. A simplified rule might look something like this. If the sender's domain is newly registered, the email contains suspicious links, and the attachment type is executable, then the email is likely to be a phishing email. These kinds of rules are easy for analysts to understand because they resemble the logic that security professionals already use when manually analyzing suspicious emails. This interpretability is one reason decision trees are commonly used in security systems and in automated triage tools. So let me just reread that rule in the middle, make sure I read that correctly. So the example logic shown there would be if all three of the first conditions are true. If sender domain is newly registered and email contains suspicious links and attachment type is executable, then phishing risk is high. So that is the example rule logic. And then the next slide shows a visual model of the same decision tree. So the diagram on this slide illustrates how the phishing detection rules we just discussed can be represented as a decision tree structure. Instead of writing the logic as a long list of rules, the model organizes the decision process into a sequence of branching questions. The system begins at the top of the tree and evaluates one feature at a time. For example, it might first check whether the email contains suspicious links. Depending on the answer, the model follows a different branch and evaluates additional features such as domain age or attachment type. By progressively narrowing the possibilities, the tree eventually reaches a leaf node that indicates the predicted risk level. high fishing risk or moderate risk. The visual didn't translate great to the PowerPoint slide, but basically, if it's no to all of those, if it's yes to all of those, it's going to be high fishing risk. If it's a mixture of yes and no, that might be moderate risk. If everything is no, it might be very low risk, for example. But this gives you sort of the overview of what a decision tree could look like, and then you would just have to refine the logic on it. And so basically, this visual representation helps explain why decision trees are often considered one of the most interpretable machine learning models. And now we said we were going to discuss overfitting later in the lecture. So let's talk about overfitting. One of the major risks in machine learning is overfitting, which occurs when a model becomes too closely tailored to the training data. Instead of learning the underlying pattern in the data, the model begins to capture random noise or accidental correlations that appear only in the training data set. Decision trees are especially susceptible to this problem because they can keep splitting the data into increasingly specific branches. If we allow the tree to grow without constraints, it may end up memorizing individual examples rather than learning meaningful patterns. To reduce overfitting, several strategies can be used. One approach is to limit how deep the tree can grow, preventing it from becoming too complex. Another approach is pruning, where parts of the tree do not improve predictive, or parts of the tree that do not improve predictive accuracy are removed or pruned out. A third strategy is to combine multiple trees into an ensemble model, such as a random forest, which can often produce more robust predictions. And another common type of supervised learning model is linear regression. In linear regression, the model attempts to predict an outcome by computing a weighted combination of input features. Each feature contributes to the final prediction through a coefficient or a weight. These weights determine how strongly each feature influences the outcome. During training, the learning algorithm adjusts these weights so that the model's predictions match the observed data as closely as possible. Although the mathematics behind linear regression can become complex, the basic idea is straightforward. The model tries to find a line or surface that best fits the data. Once that relationship has been learned, the model can apply it to new examples in order to make predictions. And then next we'll talk about a linear classifier. A linear classifier adapts the same basic idea used in linear regression, but applies it to classification problems. Instead of predicting a numeric value, the model attempts to determine which category an example belongs to. The model computes a weighted sum of the input features. That value is then passed through an activation function that determines which class should be predicted. A very simple activation function is a step function, which outputs one class if the value is above a threshold and another class if it is below that threshold. Conceptually, this means the model is drawing a boundary in the feature space that separates one category from another. Everything on one side of the boundary is classified as one class, and everything on the other side is classified as the other class. In many practical systems, the simple step function is replaced with a smoother function called the sigmoid or logistic function. Instead of producing a strict yes or no decision, the sigmoid function outputs a value between 0 and 1. This value can be interpreted as a probability estimate. For example, the model might estimate that an email has a 0.9 probability of being a phishing email, or that a file has a 0.7 probability of being malicious. Because the sigmoid function is smooth and differentiable, it can be optimized using algorithms such as gradient descent. This makes it especially useful in machine learning systems that learn by gradually adjusting their parameters during training. And so here's an example of a probability scoring in security systems. So many real-world security systems do not produce simple yes or no answers. Instead, they generate risk scores that represent the probability that an event is malicious. Logistic models are commonly used to produce these probability estimates. For example, an email filtering system might assign a phishing probability of 0.91 to a suspicious message. A malware detection system might estimate that a file has an 83% chance of being malicious. Fraud detection systems often produce similar probability scores for suspicious financial transactions. And security tools then use these probabilities to guide decisions. High-risk events might be automatically blocked. Moderate risk events might be flagged for investigation, and low-risk events may be allowed to proceed. This probabilistic approach helps balance security protection with the need to minimize false positives. And we talked about overfitting earlier, and we're going to go into a little more detail now on overfitting. So overfitting occurs when a machine learning model begins to capture noise or accidental patterns in the training data instead of learning the underlying relationship that generalizes to new situations. When this happens, the model performs extremely well on the data it was trained on, but performs poorly on new data. This problem often arises when the model becomes too complex relative to the amount of data available. The model starts fitting every small detail in the data set, including random variation that does not represent a real pattern in the world. In cybersecurity applications, overfitting can be especially dangerous. A detection system might appear highly accurate during testing, but fail to recognize new attack variants in the real world. Because attackers constantly adapt their techniques, security models must be designed to capture general patterns of malicious behavior, not just specific examples seen during training. So now we'll talk specifically about overfitting in malware detection. A good example of overfitting occurs in malware detection systems. Imagine a model that is trained on a collection of known malware samples. If the model focuses too heavily on specific byte patterns or signatures present in those samples, it may appear highly accurate during training. However, attackers frequently create new malware variants that make small changes to their code in order to evade detection. If the model has memorized specific details of the training samples, rather than learning broader behavioral patterns, it may fail to recognize these new variants. Effective malware detection models, therefore, focus on general features, such as behavioral indicators or structural characteristics of malicious software. By learning broader patterns instead of memorizing individual examples, the model is more likely to detect previously unseen threats. And this slide illustrates how increasing model complexity can lead to overfitting. The graph shows several models with different levels of complexity attempting to fit the same set of data points. A very simple model may not capture the underlying pattern well, resulting in underfitting, and underfitting is where the model is too simple to explain the data. As the model becomes more complex, it may fit the training data better and better. However, if the model becomes excessively complex, it may begin to follow every fluctuation in the training data. At that point, it is no longer capturing the true pattern, but instead modeling random noise. Such a model may appear highly accurate on the training data, but perform poorly when applied to new data. So that shows both underfitting and overfitting, the two extremes. Now, test set error can arise from several different sources. One major factor is bias, which occurs when the model is too simple to represent the true relationship in the data. And that can include representation bias or search bias. And then another factor is variance, which occurs when the model is too sensitive to the particular examples in the training data set. So these two sources of error create what is known as the bias-variance trade-off. Simpler models tend to have higher bias but lower variance, while more complex models tend to have lower bias but higher variance. The goal in machine learning is to find a balance between these two extremes. A good model is complex enough to capture meaningful patterns, but not so complex that it overfits the training data. And then finally, cross-validation is a technique used to evaluate machine learning models more reliably, especially when the available data set is limited. Instead of dividing the data into just one training set and one test set, cross-validation repeatedly splits the data into different training and validation subsets. In each iteration, the model is trained on one portion of the data and evaluated on another portion that was not used during training. By repeating this process multiple times, we obtain a more reliable estimate of how the model will perform on new data. This method is widely used in practice because it helps ensure that evaluation results are not overly dependent on a single arbitrary data split. For cybersecurity applications, where data sets may be limited or highly variable, cross-validation provides a more robust way to assess whether a detection model will perform well in real-world conditions. And that concludes the slides that I have for you on Chapter 7.